for this carbon 60 stuff, this is the carbon 60 in ball and stick model. Okay, you can easily see that there are hexagonal stuff. Okay, but if you only live on an XY plane, you will have hexagonal all the way, only hexagonal. That is called graphene. In Chinese, is set hey. Okay, 石墨烯. Okay, but in order to make it into a sphere, unavoidably you need some pentagonal stuff. Okay, so it is not obvious that you need that, but the soccer ball people know that very early on, because every soccer ball has such a thing. Okay. If we only have carbon strictly on a two-dimensional sheet, it is what people call graphene, and that is another Nobel Prize winning. Also, it's not difficult to win a Nobel Prize. How they got this thing is very simple. They use pencil. So you just take a pencil. Okay, you have this so-called lead, but it's not lead, it's carbon, it's graphite. Okay, and then this Nobel laureate did the following: use some Scotch tape, stick to the lead, and get something out. Okay, now it is certain that you have some carbon sheets of graphite there. The next thing they do is throw the Scotch tape together, pull it out again. Okay, so what they are doing is they actually don't know how many layers they pulled out, so they use the Scotch tape trying to thin them out. Okay, pull again so that maybe 4 layers now, both sides are 2 layers, and then repeat it and repeat it, and they claim at the end, after several times, there must have some single layer graphite sheet on your Scotch tape. So of course they have fancy experimental tool like optical transmission experiment, so that they can see, really in this region I get a single layer, and that is called graphene. And graphene has this structure. Okay, again, a lot of sp2 hybridized orbital forming all these bonds. But remember, the carbon, if they do sp2, there's always a pz still not involved in bonding. Then you can think that every atom has such a thing sticking in and out of the xy plane, and then what happened to them? They can, just like what we discussed, they could delocalize themselves living on this graphite. And very interestingly, what happened to them is the following. That can be calculated through solid state physics, and experimentally, many works have been done on that. So this pz electron, they are living in a periodic structure. Now, this repeat that, repeat. Okay, so this is periodic structure. That is to say, it is a 2D solid. It is solid state physics in 2 dimensions. So therefore, we can try to understand so-called their behavior, their band structure, okay? But I don't want to introduce band structure, but in a very easy term, we want to discuss the energy momentum behavior. For free electron, in the typical behavior, we would expect p squared over 2m, right? For free electron. This is Newtonian type, half mv squared, okay? But let me tell you, for this graphene 2pz electron, their energy momentum behavior is very peculiar, very special. They behave like linear. So here I draw a energy px, py, because it's just 2-dimension, okay, behavior picture for you. You see, you have this cone. It's like one of those, you take it and drink water in clinics, you know, those paper cone, okay? So you take one of this, and this is this shape. I draw another one because in solid state physics, we will have many bands. So this is one band, this is another band. And now we have electrons. So after we fill all the electrons in, the electrons completely fill the lower cone and leaving the upper cone completely empty. However, these two cones just touch at one point, all right? Now that is the behavior that we understand. We can use solid state physics to understand this behavior. But the peculiar thing about graphene electrons behavior is that it has this linear, now you see this linear line behavior. So in a way, they are like, in a fancy term, massless fermion for the following reason, okay? You know, relativistically, you have this, right? If the mass is 0, but they are electrons, they are real electrons. But if the mass is 0, then you have this behavior. And it is this behavior being observed for the electrons living on the graphene sheet. And more, if you roll up the graphene sheet, you will get something called carbon nanotube. Now this is a carbon nanotube. Let me show you the, whoa, okay. So this is another very fascinating topic in research. Here it may be just maybe 10 angstrom apart, okay? And then you have this nanoscale. You may think about putting something, some other nanoparticles into it, and this form a way to transport things in a nanocircuit, okay? So you have this nano technology. This whole thing is like hexagonals, but just rolled up, okay? sp2, carbon, carbon, carbon. You just roll it up, and then you get this thing too, okay? You can even put a carbon 60 in it, okay? So for the remaining section, let's move on to the last example of hybridization. Another Nobel Prize winning stuff, sp3 hybridization. This is important because the most useful and the most money-making materials make use of this sp3 hybridization. We use a simple example first, CH4. Okay, I think that answered a previous question about why don't we include PZ consideration in C2H4, okay? My answer at that time was we don't have enough hydrogen to do more bonding, okay? And now look at this case. I have only one carbon, but it's bonding with 4 hydrogen, and that exists, okay? I mean, this thing exists, real thing. So we have something to explain. Again, looking at this carbon electronic structure with our experience, we should start with something like that. Now, it becomes possible to bond to 4 hydrogen because we have 4 states each with an electron in, and 4 hydrogen each with its own electron can pair up and form 4 bonds. But immediately you also see they should be equally strong. I mean the 4 bonds, right? Because it's one thing with 4 same thing, right? So how come? That motivated us to do another exercise very similarly. This time, 1 s orbital and 3 p orbitals now form linear combinations 4 in, 4 out. Therefore, we are making 4 linear combinations. That can be our old Z as well. Okay, if you want to make connection, you may call it CI. I is 1, 2, 3, 4. Okay, so I also know that this S must be shared among these 4 hybridized orbital, and it will not bias any one of them. So there will be 25% S character in each one of them, probability-wise. So the amplitude, the probability amplitude before squaring it will be 1 over square root 4. It is a half. Okay. So with this, I don't need to solve for 16 unknowns. Instead, I only need to solve for 12 unknowns. Okay. Again, you can play the game. I put one of them in one direction, and then I start look for the remaining ones by normalization. I mean, each one of these should be normalized, and then they are mutually orthogonal. So you have many orthogonality conditions that will be sufficient for you to solve for all the remaining coefficients. Okay? I'm not going to repeat this here. Just write down the result for you. So this is the result. This 1/2 comes from this, okay? But then all the coefficient after solving it will be something like this, okay? But the signs are different, okay? Now, first of all, this is one way to write it out. Just as the sp2, after you do that, you can rotate the thing around, okay? The shape is, this is the nucleus. The 4 hybridized sp3 orbitals form a tetrahedron, okay? And then a special angle between neighboring sp3 orbitals. It is 109.5. This week, one of the sample questions, the TA will calculate this out for you, okay? Let's look at this 4 resulting sp3 hybridized orbitals. Again, the lazy way to look at the direction is the following. You think of it as a unit vector in x, y, z. So this is like 1, 1, 1 in x, y, z. So it's pointing in the diagonal. You have an x, y, z set up. So the first one will be placed there. Okay. Similarly, you put the other 3 -1, -1, +1. So it's one direction, and then so on. Okay. And at the end, you will plot out something like this, but now only it is rotated with 1 towards the 1, 1, 1 direction in your x, y, z coordinate. Okay, so that is the idea. So at the end, after doing that, it can bond with 4 hydrogen. The quantum physics is now very easy. You don't need to consider the whole thing at once because already did the linear combination. This will be highly concentrated to overlap with the H. So it is like a 2 by 2, 2 by 2, 2 by 2, 2 by 2, decoupled. Okay, that is why we want to do the linear combination at the beginning. Therefore, pushing up, pushing down, occupying the lower one of guarantee energy is gained. And that is how this CH4 is formed with such a structure. Again, this is the standard 109.5 degree. But more importantly, this shape, tetrahedron shape, can be propagated outward to form solids. And there are many useful examples. So on the left, think about it as carbon. Everything is carbon, no more hydrogen, okay? So this carbon is surrounded by 1, 2, 3, 4, okay? In exactly the same tetrahedral way, this way, only rotated, okay? Not only that, this one is again surrounded by 4, but the other 3 is outside this box called unit cell that we drew, okay? So with this, that can propagate into a big chunk of material. And in doing so, this type of carbon can sell a lot of money. For a lot of money, it's called diamond. Okay? Rather unusually, but if you understand it is usual, that not only carbon, but silicon also have this structure. So every dot here is a silicon atom. Therefore, silicon also formed with the silicon crystal using sp3 hybridization, the same thing. Also, germanium. Okay, so let me tell you that silicon and germanium are the 2 most useful elemental semiconductor. By elemental, we mean the semiconductor is formed by one single element, silicon. So all are silicon atoms, all are germanium atoms, all are carbon, okay? But the diamond is not a semiconductor. The diamond LUMO-HOMO gap is very big. I think the diamond LUMO-HOMO gap is more than 5 eV. And that's why it's transparent. You make the connection, right? The gap is that big. Electrons are occupied down here. They're all empty up there. But the gap is 5 eV, more than that, okay? So visible light come in, the electron cannot absorb it. If they absorb it, they have nowhere to go. The empty state is that high. But visible light is about 1.5 eV. Can't do anything, okay? So they will not absorb. So you have this very shiny, very nicely looking diamond, okay? So if you think about it, should it cost that much? Well, in terms of physics, it's just having a big gap. Solid state physics is the same as silicon. Silicon, you can find it on the beach. Those are silicon dioxide, okay? So why one thing is so cheap, one thing is that costly? Well, of course, diamond is very difficult to make. It's highly unusual. You need high pressure so as to form this particular shape. Graphite is another type of a carbon crystal, and that is much cheaper. It's easier to make. Okay. So, but these two are the most important material nowadays, because your phone, a lot of silicon industry, supporting our life, your PC, your mobile phone. And in recent days, there's shortage of silicon wafer in the world. So many phone companies are cutting back their production line, the schedule. They have no raw materials to do, okay? So to work with. So you now understand how silicon, how important is silicon, okay? But for us, nothing fancy. It is just, let me see, do I have a, okay? So it's just something like this, okay? So this is, now if you don't look at it as two different colors, then this is diamond. This is diamond, nothing more than that, okay? I even have some, draw out a cube for you to look at, okay? That cube is the picture that I just showed you. Of course, in the diamond, you don't see these lines, this cube. They just arrange themselves in such a unit cell, all right? And you can see, if you, let me see, can I see it from my monitor? Yeah, barely. For example, this side, this side, this side, this one, okay? So this one, you have a nearest neighbor here, okay? And then you have a nearest neighbor there, okay? And then you have the nearest neighbor there, okay? Go back to the center. There's another one that is backward here, okay? So that is forming this, let me rotate it for you. Now I see the difficulty. It's like a mirror to me. When I do left, it's my right. Oh, that is the zoom problem. I'm not looking, I'm looking in a mirror. Very strange. Okay, so I hope that you now, if you come to my office to pick up your midterm exam, then I can show you, okay? So that's actually here. But this is the diamond structure. And more, the most useful compound semiconductor is gallium arsenide. And this is of the same structure. Now you can look at the black dot, one color as a gallium atom, the other color as an arsenide atom. And this is the same structure as silicon, okay? So again, you see this sp3. Hybridization is affecting our life in a very important way. In an increasingly important way, I would say. So this is the right-hand side picture, okay? When you have two different atoms, this structure is called zinc-brand structure for particular example, okay? This one is called diamond structure, although it also works for silicon germanium. Of course, for diamond, this length is one number. For silicon, this length is another number. They will have different preferred separations. We know how this comes from, right? Electrons distribute themselves to form the bond. They govern the separation between nearest neighboring atoms. Okay, quantum mechanics. And even this structure, this sp3 tetrahedron structure can propagate into other crystal structure. This is called Wu-side structure. I have it here. Okay. All right. So again, you can easily see this. You look at one dot, this one, okay? Then immediately you see there's some neighbors up there. Let me try this one, but this one is easy, okay? This one, you see a neighbor up there, you see a neighbor towards you, there's a neighbor on this side, there's another neighbor on this side, again, in this typical tetrahedron shape. And propagate out, it forms this structure, okay? This is called a Wu-side structure, again, depending on sp3 hybridization only. And what is that important? And another Nobel Prize winning stuff. In 2014, a recent Nobel Prize, it was awarded to the work of discovering gallium nitride as a blue light emitting semiconductor. Because before this work, well, that work started in the 1990s. Before that work, we only have the red and the green. So when you go onto the street, those big board trying to show you advertisement, movies, things like that, lack one color. The materials, the semiconductor has not been found, okay? So 3 Japanese researchers somehow very simply, you can pick up the phone and order this material, but only no one before them test sufficiently well or can mass produce them, okay? So this has this structure and it emits blue on the high, around 3 eV side, 2 point something to 3 eV side of light. So now we have all the colors around, we have very good display, digital display on the street. Even under strong, bright sunlight, we can still see this thing very clearly, okay? So this is another Nobel Prize awarded. So the take-home message of this whole module up to here, the next part is about letting the atoms vibrate again. Okay, we will have vibration and rotation of the molecule. But up to here, we study the electrons' contribution to bonding. The take-home messages are, what we learn in quantum mechanics, if we apply it cleverly, okay? So can be used to understand a lot of things, including all kinds of bonding. So we see quantum mechanics, LCAO-MO, as an approximation to solve the electronic problem, together with variational method, some very simple 2x2, often 2x2 matrix, because 1 atom, 2 atom bond, push, fill, energy gained, bonding, done, okay? If you understand every single word I said, you are in good shape, okay? You see, nothing fancy, but the impact to the knowledge of humankind is really big, because only that we understand the world of materials, meaning periodic table, all compounds, and bigger molecules called solids. I think that is 99% of the world we encounter, right? You don't see neutron, right? You don't see proton, I think, right? You don't see quarks. Of course, those are very fascinating things, but I think the bigger ones are equally fascinating. Even nowadays, many people are trying to use quantum mechanics to understand biomolecules, the molecules of life. But those are very big ones that's very hard to do much quantum mechanics calculation on it. We know the equation, we can't solve it, okay? but people are using bigger and bigger computing power to try to understand biomolecules these days. And then we also are able to put the binding of things. We don't need to preoccupied by this is ionic bond, this is covalent bond, this is metallic bond, things like that. We have one umbrella idea. Schrödinger equation solve it. Okay, LCAO should be a good thing. Okay, then we understand binding, all kinds of them, hybridization, sigma bond pi bond, the delocalization of the pi electron, all under quantum mechanics. And that's rather profound. And then the whole idea, I think the whole point of my course here is that a little idea, not much. You don't need to learn one thing to explain one scenario. Only a little idea, but you need a solid understanding of it, can do a lot of things. You can understand a lot of nature by a small idea, okay? And then I would like to introduce the people I already did last time. Mulliken and Hun did a big part of this MO theory so that we understand bonding. Mulliken got the Nobel Prize, Hun did not. And I would end this part with this very famous passage written in a paper by Dirac. Dirac did a lot of this kind of physics. Okay, so don't think about Dirac is Dirac equation, QED. Of course, he contributed that, he established that. But at the beginning, he also did many electron systems, meaning molecule and solid systems. Okay, so this is one of his famous papers before he got the Nobel Prize, 1929. This is after he got the Dirac equation, 1927. Then he was trying to understand what happened if there are many electrons in the system. Okay, his Dirac equation is single electron. His first paper, 1926, in quantum mechanics is about commutator. X, P is IH bar, what we call the Poisson bracket in classical mechanics of position and momentum. Okay, that is one. So XP commutator is IH bar. That is his first big contribution. So in 1929, in this particular paper, Quantum Mechanics of Many Electron System, I would like to call your attention to the introductory very first paragraph. It is in full Dirac style. So let me read you the passage. He says, the general theory of quantum mechanics is now almost complete. 1929, okay? The imperfections that still remain, so the remaining work to do, being in connection with the exact fitting in of the theory with relativity ideas. So he see one thing, maybe how this Schrödinger style thing to go in line with relativity may be a problem, okay? But he already contributed to it. He wrote down the Dirac equation. And then this gives rise to difficulties only when high-speed particles are involved and are therefore, now that is about atoms, molecules, and solids, therefore of no importance in the consideration of atomic and molecular structure and also ordinary chemical reactions. You see, Dirac wrote about he thought about chemical reactions. So you should also do that, right? Down to earth thing. Do you know that Dirac's first degree is an engineering degree? And after that, he did a PhD in Cambridge in theoretical physics. Okay. And about this problems, atoms, molecules, and chemical reaction problems, he said, in which it is indeed usually sufficiently accurate if one neglects relativity, variation of mass with velocity, okay? And it's sufficient to assume only Coulomb forces between the electrons and atomic nuclei are important. That is his viewpoint. And this go in line with the title of the paper, Many Electron Systems. He wants to discuss how to deal with many electron systems. And the second sentence, the next sentence is what I want you to notice. The underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known. And the difficulty is only that the exact application of these laws lead to equations much too complicated to be solvable. Okay, so what remains to do? It therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed. This is exactly what we have been doing in this course. Developing approximation and practical methods, okay? To apply quantum mechanics to understand atoms and molecules, okay? And derive great insight, which can lead to explanation of the main features of complex atomic systems without doing too much computation, without doing much calculations, okay? So I really encourage students to reread this passage and appreciate a great mathematical physicist, Dirac, what he was thinking at the time there about the situation of physics and about the progress of physics and what should be done for physics and what should be done for quantum mechanics in order to understand nature, okay? Let me end with this very set highlight passage. He regarded 100% chemistry was understood and a big part of physics is also understood. That means there's a remaining part not understood. Of course, we know that those has to do with strong interaction, weak interaction, or gravity, and how to get gravity into quantum mechanics. A lot of things that is nowadays at the frontiers, okay? So you should really appreciate what the course here is designed for. And actually, we have used very small ideas, but using them skillfully together with some approximation skill, and we were able to understand the periodic table, a lot of physics there, and also bonding, the structure of molecules. So this is the end of this first part. We have a second part of the molecular physics that has to do with vibration and rotation of the molecules and how we plot this vibration and rotational property of molecules. They will show up in something called molecular spectrum. And that will be the last part of our course, okay? So long for now. I will see you next Tuesday. There will be one more assignment. I want to write it up this weekend, okay? So I will email it to you when I have set it up, okay? So bye for now.